Hi guys, so this week we're looking at nuclear magnetic resonance or NMR spectroscopy. So we'll begin with the basic principle of NMR spectroscopy. So we're still using our electromagnetic spectrum, and this time we're now in the radio frequency region. And the radiation from this region is used to excite your atoms. Typically we're dealing with protons, okay, so the 1H isotope or carbon-13 atoms. We focus on our protons for the moment. When we're talking about their spin, it's typically random, okay, so it moves in any direction, and this is when there's no external magnetic field applied. But in an NMR instrument, we do apply an external magnetic field. And what happens is when this external magnetic field is applied, the protons can align their spins with or against the external magnetic field. So we have our little images here just representing that. So see, typically without their external magnetic field, their spins are all over the place, randomly orientated. And then once we apply our magnetic field, their spin will either align with the magnetic field or against it, okay? And this B0, this is a shorthand notation for our magnetic field. And the range of frequencies that is required for the excitation of these protons is really characteristic of the chemical structure of the molecule. So NMR spectroscopy is actually the only technique that we've covered so far that will give us the exact detail of what is in a molecular structure and where. So we'll look at that a bit later on. So we've said that our 1H and our carbon-13 are, say, the most common kind of isotopes that we'd use, okay, but we can also have a few others, okay, so we've just listed them here. And these are basically act as though they are like a magnetic vector, okay, so they're spinning and they have certain properties there. So we've already said, so when the external magnetic field is applied, protons can align their spins with or against it, and the difference between the spin being aligned with the field or being against the field will depend on the strength of the magnetic field applied. So different instruments, different NMR instruments can have different strengths of magnetic field. So some will be a little bit weaker and some will be a lot stronger. So typically around 500 megahertz is a nice kind of one to have. So we can use an equation to determine the energy difference, okay? So just for your general knowledge more so, okay, we won't be putting this into practice now because we don't have to, okay? All of this kind of stuff is obviously computerized at this point, so we don't really rely on these actively in the lab when we're doing characterization. Okay, but we can have, so delta E, so the change in energy is equal to Planck's constant times gamma, which is the magnetodiarc ratio of the particular nucleus, and then your external magnetic field. Okay, so your B0. And that will give you your energy difference calculated. So again, we're still on our electromagnetic spectrum. We've already looked at our IR, so we've looked at our near IR, we looked at our UV and our visible regions, we looked at fluorimetry, and now we're moving up this way, okay? So we're increasing our wavelength, so we're up in the microwave radio region now, okay, so in our NMR, and it is lower energy, okay. So unlike our other methods used, the energy between the ground state, okay, and the excited state, or the energy required to move a proton here from a ground to excited state, is not large. So the wavelength of the energy used in NMR is of lower energy, and therefore we are in the radio frequency region. And the units we're using this time are now hertz, okay, so it's a unit of frequency. So again, the stronger the magnetic field applied, the greater the radiation frequency, or the shorter the wavelength required to cause the spin of the nucleus to align against the magnetic field. Okay, so that's what's happening down at that subatomic level and what's actually causing our spectra to form. So again, when we're describing our NMR instruments, we're typically describing them in terms of frequency at which they cause the protons to resonate. So therefore, if we had a 600 megahertz instrument, it would cause your protons to resonate at a frequency of approximately 600 megahertz. The higher the frequency, the greater the sensitivity. So therefore we want ideally to have an instrument that is of higher frequency. And this becomes particularly important when we're dealing with samples that may be a little bit more dilute and a little bit less soluble, that kind of thing. So if we compared an instrument that had relatively low frequency to one that had relatively high frequency. So 16 megahertz instrument would be an instrument of very low frequency. And the population differences, okay, for your ground state and your excited state for a proton is roughly 1 in 100,000. Whereas if you have a 600 megahertz instrument, the population difference is roughly 1 in 10,000. So you have a tenfold increase in your sensitivity there. And that makes a marked difference when you're doing any form of sample analysis, again, particularly as your spectra get more complex and as you're dealing with compounds that are maybe rarer, higher value, or again, maybe lacking certain characteristics such as your solubility. So this is our general layout for instrumentation, okay? So typically what we have is, we go through here, so this in the center here is our sample vial, okay? So usually these long, narrow glass tubes, and we'd have our compound of interest, which has to be solubilized in a particular type of solvent, so it's something known as a deuterated solvent. And in NMR we can only work in the liquid state, okay? So anything we're working with has to be solubilized first. Then we have our throughout the whole time that this is being analysed in the instrument, it's going to be spinning, okay? And this is to make sure that there's an even application of the magnetism within the instrument, okay? So we'll have our magnetic poles here, we have sweeper coils. Whatever signal is being generated then, we will be able to detect it, okay? So it'll be received and it'll be amplified, and then obviously it goes straight to our computer where we'll actually be able to see our spectrum. And again, obviously, this is all computerized, and the raw data from the instrument undergoes further transformation, and we can then see it as a proper graph, okay? So what would we actually do? So if we were going to use the instrument, how would it work? So I've already said that we take typically our solid or liquid sample, and we'd, either way, if it was solid or liquid, we'd have to put it into deuterated solvent, okay? So deuterated solvent is the solvent in which any hydrogens have been replaced with deuterium, and that isn't NMR active. So we take those, we pop them in our NMR tubes. When we're handling our NMR tubes, we're extremely careful, so wearing gloves, and this isn't to, that it is to protect us, but it's also to make sure that we don't have any interference with our sample. So lovely clean tubes, we make sure that they're bone dry, so we typically, before using them, you'd wash them very well with, if you have something particularly sticky in it beforehand, you'd do an acid wash, you'd wash it thoroughly with water, then with acetone, and you'd leave them to dry in an oven or furnace to allow them to be completely dry, because you don't want any overlap or any contamination of your sample with something that's been used to clean it or a sample previous to it. We then take it, we pop it in a spinner, and we would place it in the instrument, okay? So then it's spun in the fixed magnetic field for about 30 revolutions, and this is done using an air turbine, and again, this is because we want uniformity of the magnetic field around the sample. Typically, when we're running these, we'd also use a reference sample, okay? So tetramethylsilane, or TMS. And this has a frequency, okay, or appears at around 0 parts per million. So that's along our x-axis of our NMR spectrum. And again, this just helps us, I suppose, compare within the spectrum, okay? So again, if we didn't see, and also to make sure that our instrument is working correctly, because if we see TMS appearing at 10 parts per million instead of 0, we know something's wrong, we need to go back and check it. So we use this as a reference. To obtain a proton spectrum, so this is dealing with our 1H, okay, or 1 hydrogen, the radio frequency is swept across a range from about 0 to 10 parts per million, say on a 100 millihertz instrument, or across 6,000 hertz. Then what happens is we have a receiver coil, so this is measuring the emission. So again, if you think we had a a proton of interest, we've excited it, it's gone from its ground state to its excited state, and on the way back down now it's emitted some radiation, and that's what we're detecting here. Okay, so the emission of radiation, the frequency, is being swept across the range. So as well as determine the frequency of the proton, the instrument will also determine the area of each signal, and we'll talk a little bit about that later on. And all of this data is gathered and it undergoes a Fourier transformation, and then it's all combined to produce a spectrum which we can then see and analyse, and each peak then will correspond to particular protons. I mentioned a moment ago that when we're doing any of this on inner sample prep, we use deuterated solvents, and we said that this is where the hydrogens within the solvent are replaced with deuterium, which is an isotope of hydrogen. And the reason for this is, particularly when we're doing proton NMR, the protons within a regular solvent would also be detected, okay? And since you're diluting a small amount of sample, typically in a larger volume of solvent, if we just use a regular solvent, our solvent peaks and the hydrogens from our solvent would greatly take over the spectrum, okay? And we'd see very, very small peaks for our actual sample protons, and we'd see a massive, massive peak for our solvent. So that's just something to keep in mind. So deuteration isn't always going to be 100%, and also depending on how well you store your solvents, you may actually still get a signal for protons coming from the solvent. However, this is typically going to be far smaller than if a non-deuterated solvent was used. Okay? And these are just some examples of them, okay? So some of the most common deuterated solvents that we use is deuterated water, chloroform D, methanol, dimethyl sulfoxide, dichloromethane, and acetonitrile. So these are the most common ones we use. And again, any hydrogens are typically in their structures is replaced with deuterium. Sometimes, as I said, we still will get a peak for them in our spectra, and again, this and in combination with our TMS, we can typically use those to recognise or just make sure that we know that they're appearing at the same frequency that they should be appearing, okay? And also they'll have a very characteristic multiplicity, okay? So that's how their peaks split. So water, for example, will just have this one broad peak. Same for chloroform, but we see it's a lot sharper. When we see methanol, we start to see a lot more multiplicity. So we have 1, 2, 3, 4, 5 peaks here. Okay, so this is known as a quintet. Dimethyl sulfoxide, again we have a quintet, but again far broader. Dichloromethane, we have 3 singlets, and we have acetonitrile here, again quite broad, but we have a quintet here. And again, this just allows us just an additional piece of information in our spectrum. We can also see where on our x-axis that they should be appearing. Okay, so water, so solvent peak for water would typically appear around 4.79 parts per million. So again, we can use this information, and we can use our solvent peak to kind of guide our spectra as well when we're doing our processing later on. So we'll have a chat about that in the lab next week when we're looking at some spectra. Your chloroform is 7.26 parts per million. Dimethyl sulfoxide will always appear around 2.5. What I've done is, as a kind of supplementary piece of information, I've left a table for your commonly used solvents and the peaks at which they appear on the Moodle page. Going forward, if you're ever doing NMR spectroscopy, it's something that is always used in the lab, so it's nice to have it. So when we're talking about a proton NMR spectrum, what kind of information can we actually get from it? So when we're talking about our position of our signals, that tells us what type of hydrogens a molecule has. When we talk about the number of signals, that will tell us how many different types of hydrogen we have in a molecule. When we're talking about the intensity of the signals, that will tell us relatively how many of each type of hydrogen we'll have in the molecule. And then when we have spin-spin splitting or multiplicity, This gives more information about the neighbouring environment for the various hydrogens in the molecule. So we'll work our way through these, but typically these are the 4 pieces of information that we have from a spectrum, and all of these can be used in tandem to figure out the exact structure of a molecule. So this is our typical NMR spectrum. So we'll just take a moment here, okay? So again, on our x-axis, and when we're talking about proton NMR, typically from 0 to 10, it can also go from 0 to 14 parts per million, okay? So that's a typical range you're looking for. On our y-axis, we're looking at intensity, okay? So intensity of the peaks themselves. Some of the terminology for when we're describing our NMR spectra. So high field is when we're closer to 0 parts per million. Low field for when we go obviously further down or further increase our parts per million. This can also be known as downfield or upfield. So just be aware of the different terminology. And we can see here we have something called shielded and de-shielded. And we're going to look at that in a bit more detail in the next few slides. Here we have our calibration peak, so we've already talked about our TMS, so that should always appear around 0. And again, we can use our solvent peaks as a calibration peak as well, because again, these shouldn't fluctuate too much in their actual, positioning here on this x-axis. But this is our general spectrum. This is what it would look like, okay? Obviously we haven't got our key peaks of interest, but we'll start to look at some spectra now. So when we're talking about proton spectrum, we are talking about our chemical shifts. So typically we've said in organic compounds, we're looking between 0 to 14 parts per million. The precise resonance frequency, or the parts per million, so again on your x-axis of a proton, depends on its environment, so its chemical environment, what is surrounding it, what kind of groups are surrounding it. So if we had a proton, so a hydrogen just bound to a carbon atom, it's going to be affected by the groups the carbon atom is bound to. So typically it's neighbouring carbons. One, definitely the carbon group next immediately bound to it, and sometimes up to two bonds away, okay? They may still have an impact on its chemical environment. So the chemical shift depends on the extent that the proton is either shielded or de-shielded by the groups to which it's attached. The more shielded a proton is, the higher upfield it's going to appear. Okay, so the closer to 0 it's going to appear. If it's attached to a group that de-shields it, okay, so something like an electronegative group, it will appear at a lower field, okay, or higher part per million. So when I'm saying shielding and de-shielding, what does that mean? So shielding is when we have electrons that are surrounding that nucleus, okay, surrounding that proton of interest. And as I said, typically when you have something that's shielded, it's pushed further upfield, okay, closer to 0. So this is going to be something like just a plain old CH3 group in that has a neighbouring methyl group as well, okay. So if you think of protons that are bound to a carbon, on either side of that carbon you have just more carbons and hydrogens, okay, so no difference in electronegativity. However, when we have de-shielding means that the electron density that would typically surround that nucleus has been pulled away from it, and it's been pulled away by something that's more electronegative. So we talked about electronegativity last week in the IR spectroscopy, and I provided you with an electronegativity table, so again that's there to help you here. If, for example, we compare these two groups, so you have a carbon surrounded by 4 hydrogens, okay, and so we just have plain methane here. There's no difference in electronegativity here. There's no group bound to this carbon that is more electronegative, and we can see that it's further upfield. If we take one of these hydrogens and replace it with chlorine, okay, so according to our electronegativity tables, chlorine is far more electronegative than carbon. And what it does is it pulls electrons towards itself, so therefore it de-shields lots of these hydrogens. And because of that, they are more exposed to the magnetic field and they are pushed further downfield. So what we'll begin to find is, as we go through some example spectra, we will find that when you have electronegative groups like chlorine, fluorine, bromine, iodine, oxygen and nitrogen, whenever we have those in our structure, we will typically see the hydrogens that are neighbouring them pushed further down. Okay, so that's the trend we're kind of looking at. These are approximate chemical shifts. Okay, so I will, in the next slide, we'll see a little table that maybe gives a little bit more detail, but typically these are the regions we're looking at. So something like an alkyl proton. So this is just your CH3 groups, your CH2 groups, and they're not bound to anything electronegative. Then we're typically going to find them between 0.2 and 2 parts per million. Protons on those groups are now attached to an electronegative neighbour. So again, your oxygen, nitrogen, fluorine, chlorine, your cyanide bond or C double bond O bond or carbonyl group, you're going to find those between 2 and 5. When you have protons that are bound directly to a carbon double bond carbon, okay, so that double bond is having an impact there. We're going to find those between 4 and 7 parts per million. And then when we have aromatic rings, okay, something like benzene, there's a very distinct region between 6 and 9 parts per million that when we're talking about aromatic rings, we should automatically be looking in that region, because we're definitely going to find the protons on those aromatic rings within that region. And this is just a little guide, okay, so similar to what we'd have with our IOR tables, okay, that we can kind of estimate where we might find our certain peaks. This is the same thing, okay, so in NMR we can predict where we may find those peaks. So again, when we're looking at alkyl groups, okay, with no electronegative groups neighbouring them, we'll find them fairly close to 0. As we start to introduce double or triple bonds, as we start to introduce groups like halides and oxygens, we'll see that they start to move a little bit further down. We have our aromatic region here, okay, between 6 and 9. Same with our phenols here as well. Our amides, okay, so your NHs, again, typically you're going to find those in this area too. And then, of course, anything that's bound to something like quite strong, and we're talking just more so hydrogens bound to oxygen, so in carboxylic acids and aldehydes and alcohols, they're going to be found much further down this way, so downfield. So this is a very, very useful piece of information to have, and definitely worth familiarising yourself with this, because this is the type of information we need when we are interpreting our NMR spectra. When we're talking, or another thing we need to take into consideration when we're looking at our NMR spectra is something called chemical equivalency. And this is basically identifying within a molecular structure what hydrogens are in the same chemical environment. If they're in the same chemical environment, they're going to have the same chemical shift on the NMR spectrum, and therefore they become known as chemically equivalent. So a few little key points here are protons in a symmetrical molecule. They're typically going to be considered chemically equivalent because, again, they are in similar chemical environments. If we have something like a proton that's beside a chiral center, okay, so chiral center or stereogenic center is a carbon that has four entirely different groups bound to it. So if you look at a structure and you find that your protons of interest are next to a chiral center, they are no longer going to be considered equivalent because that chiral center will have an impact on the individual hydrogen's chemical environment. We use equivalency when predicting the number of peaks on our NMR spectrum. And there's a lovely video now from Khan Academy, so I've added that onto the Moodle page, so I'd like you to go watch that first, and we'll continue on with the rest of the lecture then.